Welcome, everyone. My name is Albert Marroquin, and I am the Dynamics Division Manager here at ETAP. I will be your presenter today. I have been with ETAP for over 16 years, and I have worked on many Dynamics and ArcFlash product design and development. It is my pleasure today to be able to present today's webinar topic, which is the Characteristics and Applications Series, Part 2, Machine Dynamic Behavior. This session is a follow-up to the one started in Part 1 by Dr. Farouk Shuku, President and CEO of ETAP. Before we get started on the content of today's presentation, I would like to give you a brief overview on the topics that we will cover today. The main emphasis will be on the effect of the parameter variation in induction motors. We will discuss how the induction motors construction affects its dynamic behavior. We will also discuss how the different models available in ETAP can help us to perform analysis of various complexity levels. Next, we will go over external starting devices and controller drives, which can be used for induction machines starting and speed control. We will also have a brief discussion of how the variation of the motor resistance and reactance can be considered to increase the accuracy of motor acceleration simulations. Without further review, let's get started on the fundamentals of induction machine dynamic behavior. The most common type of induction motor and the center of the discussion in today's webinar is the squirrel cage induction motor. It consists of a cylindrical cage interlaced with steel core laminations. The cage conductors are typically copper alloys or are made of copper alloys and or aluminum and are shorted at the ends with conductive metal rings, which help to give the cage-like shape from which it derives its name. The basic magnetic principles, which we do not have the time to go over in detail, take place in this cage-like group of loops, where Lenz's law describes that a magnetic field will be induced by the rotating magnetic field in the stator. The examples presented in this webinar throughout the duration of this particular session are all designed around the behavior of squirrel cage induction motors. Induction motors can also be of wound rotor design. The wound rotor design presents advantages because it allows the access of control of the rotor conductor winding resistance and reactance, as can be seen in this slide. By the same token, an external voltage source could be used to apply a voltage at the rotor windings through brushes. This externally controlled electrical characteristic of the rotor can help us to control the current of the motor during its operation. Common applications for wound rotor induction machines are resistance and voltage control of induction generators. Induction generators will be discussed in a future webinar with an emphasis on renewable energy technology. Next, we will take a look at the induction motor equivalent steady-state electrical circuit. From this point forward, our discussion will focus on single cage induction motors, but the basic derivations and equivalent single cage induction motor can be used to represent dual cage induction motors. The circuit shown in this slide shows the basic components most commonly considered for induction motors. We can see the stator resistance and reactance denoted by RS and XS. We have also the core resistance and magnetizing reactance denoted by RC and XM. Finally, we can see past the air gap line the resistance and reactance of the rotor bars. We also see a special term which relates the rotor resistance to the machine slip in order to determine the mechanical power delivered to the motor shaft. It is worth noting that ETAP induction motor models do not include saturation effects. Saturation is rarely modeled for transient dynamic behaviors. However, the saturation will be placed in series with the stator reactance and the rotor reactance. Like I mentioned before, the dynamic behavior of the induction motor is determined in its vast majority by using the single cage induction motor shown in the image above. We can also observe the corresponding image from the ETAP induction motor editor, right below the cage and the diagram. In ETAP, the single cage, squirrel cage induction motor is represented by the single 2 model. This is how we would find it in the ETAP library. Note that so far we have only talked about the basic component electrical circuit representation. However, we can into more detail discuss the rotor cage and bar construction. It is these two items that dominate the dynamic acceleration characteristic of the induction motors, and which are taken by electrical engineers as the norm for classifying the different types of squirrel cage induction machines. We also have other types of rotor constructions, like the double cage integrated bar design. Such double cage designs were created to allow for different rotor effective resistance during the acceleration or starting and steady state running at rate of speed of the machine. Typically, the inner cage bars are thicker and are made of material that has lower resistance. The outer bars are smaller in cross-section and have a higher resistance. They are placed near the surface of the rotors so that leakage flux sees a path of high reluctance. We will take a look at these detailed rotor bar constructions in a few minutes. During starting, the difference between the rotor and stator frequency is high, and thus there is a high leakage reactance. This leakage reactance interacts mostly with the outer bars, producing an effective high starting resistance because of the outer resistance higher resistance values. At low slip during running conditions, the leakage reactance is small, and thus the inner low resistance bars carry the majority of the current, and therefore the machine will operate at higher efficiencies during its normal operating conditions. The two cages can be connected together or can be independent, not connected together. In this case, we see a double cage independent bar design, which means that the two bars are not connected together or short-circuited at the end of the cage through slip rings. This gives the motor a slightly different torque characteristic when compared to the previous design that we observed. The circuit diagram shows the equivalent circuit of an independent double cage induction motor. In this case, the reactance of each cage is independent. There are other alternatives to the use of double cage induction motors. The single cage bar can be constructed with a narrow, deep bar with different shapes near the surface of the rotor. This effect is known in ETAP as the deep bar effect. Both the deep bar effect and the double cage rotor construction effect are accounted for in ETAP by applying either a linear or a nonlinear rotor variation as a function of the motor slip. This leads us to the following final equivalent circuit, which is used for dynamic induction motor modeling. Like I mentioned before, the dynamic behavior of the induction motor is determined in its vast majority by using the single cage induction motor shown in this diagram. Here we can see a difference from the previous diagrams. We can observe that the rotor reactance, denoted as XR, is now also a function of the slip. In the same way, the rotor resistance is now a function also of the slip. With both rotor reactance and resistance being functions of the slip, we can apply the variations in their characteristic during acceleration. These variations in D-bar construction are what engineers will use to classify the different types of squirrel cage induction motors. Some of the basic NEMA classifications of induction motors' characteristic dynamic behavior are shown in this slide. Type A and B are fairly similar and therefore can be shown in this slide as simply type B. As previously discussed, the double cage induction motor can be best approximated using the bar design of NEMA Class C as shown in this diagram. As we can see, the NEMA Design C has both an outer and an inner bar portion with higher resistivity and lower resistivity. This is what helps us accomplish the high resistance and high starting torque characteristic versus low resistance and higher efficiency during running conditions. The diagram that we have as well in this particular slide also shows a linear deep bar effect relationship that is applied to the resistance and reactance of the machine. At lock rotor conditions, in this example for a NEMA Design C motor, the rotor resistance, bar resistance will be high, and it would decrease as the motor reaches close to its synchronous speed at normal full load operating speed. In the same token, the reactance of the machine will be lower at lock rotor condition, and it will increase as it reaches its normal operating speed. The NEMA type B, which is similar to type A as I previously mentioned, are covered with the B bar design construction, so like I mentioned before, there's no need to show them both in this slide. Also, as we can see, there is information in this slide which agrees with what we have previously discussed. The cross-section area and the position on a NEMA Design B bar produces high reactance. The starting torque is normal and the starting current is low. With a NEMA Design C, we have a double deck design which approximates a double cage induction machine. The double deck with small conductor of high resistance during starting, and most current flows through the upper deck due to high reactance of the lower deck. The starting torque is high and starting current is low. The NEMA Design D bars are made of brass or similar high resistance material. Bars are close to the surface to reduce leakage reactance. The starting torque is very high and starting current is low. This slide shows the difference in rotor resistance and reactance and how each group of parameters affects the motor torque characteristics. In here we have parameters that represent a NEMA Design A and B. As we can observe, both the stator resistance and reactance are fairly similar for both machine types. However, we can start to observe some differences when it comes to the reactance and resistance of the rotor between Design A and B. The difference becomes even higher when we compare Design A to Design C and D, where in Design C we can observe a very high rotor bar resistance, and that is indicative of motors which require a very, very high starting torque requirement. In the diagram on the left hand side, we see a representative of the motor torque characteristic curve as a function of speed. The Design D motor actually shows the highest torque delivery at near lock rotor current conditions and continues to decrease as a function of speed as the load requires a higher speed variation. This type of motor would be typically applied to cranes and other similar types of loads. Next, I would like to show you how we can perform simulations and study the effects of the parameter variation. And this will include the variation in the rotor resistance and reactance, as well as the variation that occurs in the system input voltage and frequency when applied to the motor stator. These simulations will help us visualize in graphical form how each of the parameters affects the dynamic behavior of the machines. Next, we would like to take a look at a simulation for the parameters. This editor will allow us to take a look at the effect of the rotor bar construction for different types of NEMA squirrel cage motors. If we select the type A and plot it, we can observe its characteristics. In particular, we want to observe the motor torque as a function of the speed or rated speed in percent of rated RPM. We can use this to compare against the other types of NEMA type motors when we plot them together. In this particular construction, we observe a lower starting block rotor torque and a higher maximum torque point delivery, almost 2.5 to 3 times the rated torque of the motor. We can easily compare that against the type B NEMA motor and observe that as we change from a type A to a type B and apply the variation on the rotor bar construction, we would start to gain higher initial lock rotor torques and lower maximum torque points, and similar full load speed operational speeds. However, as we introduce potential double cage induction motor designs or NEMA type C bar constructions, we can observe that we have a much different motor torque characteristic. We can see that the initial torque has now increased almost 100% from the original type A design, near to 2% or 2 per unit or 200% rated torque. Last, we can observe what a type D design will look like, and similar to the previous slide where we showed the comparison of the NEMA type designs, we see that the type D motor would actually show a much higher or the highest initial lock rotor torque, and its torque characteristic will decrease as it reaches near full load speed. So this slide here, or this particular editor, allows us to visualize the effect of the different rotor bar constructions. One thing that I hadn't mentioned about the rotor type constructions as well is that their current, operational current, can vary significantly. In fact, between type A and type D, there is a significant variation of almost 200% difference between the highest demanding current type and the lowest demanding current type. This is a characteristic that is also utilized for different applications. Now let's take a look at some of the other important parameters for the effect of motors in their dynamic application. Let's look at the effect of voltage. In this case, we are starting the voltage with 1 per unit rated motor voltage. With that condition, we can observe for a type A design squirrel cage machine that it would approximately take approximately 1.5 seconds for it to reach its full load speed based on the load torque characteristic that is presented in this particular graph. If we were to reduce the voltage by 10% and apply 0.9 per unit, we would now see a proportional increase in the acceleration time and also a proportional decrease in the motor torque applied to the motor shaft. If we continue this trend, we can easily observe that a decrease in voltage produces a proportional decrease in the motor torque, and the reduction in this stator voltage will produce a difference in motor torque which is proportional to the difference of the voltage square. In this case, when we go from the original case at rated motor voltage and we compare it to the case at 0.7 per unit, we'll notice that the difference is approximately 0.7 squared, which in this case is approximately 0.5. That means that we will have reduced the available torque or starting torque of the motor by approximately 50%. Now let's take a look at what happens when we vary the frequency. If we vary the frequency, we will change a lot of the fundamental starting characteristics of the motor. In this case, we go back to our NEMA Type A design where we have both rated voltage and frequency. If we change the frequency by 5% or reduce it to 0.95 per unit, assuming the base frequency is 60 Hz, we can observe that the machine will demand higher current, as denoted in this upper right hand corner graph, where we see that there is a significant increase in the current drawn by the motor. This is obvious because of the lower effective reactance of the machine under lower frequency conditions. At the same time, we start to notice that the motor torque shifts its maximum torque point towards the left, and it continues to do so as we lower the frequency even further. If we go to 0.9, we start to notice a trend, the same similar trend, and finally if we lower the frequency down to 0.8 per unit, we will observe what is the effect on the motor torque. At the same time, we can also observe the effect on the motor speed. We can observe that the speed of the motor is directly proportional to the synchronous reference frequency or the base frequency. In this case, since we're applying 0.8 of the frequency, the motor rated RPM will go down to approximately 0.8 of its base revolutions per minute value. At the same time, we'll notice that the available acceleration torque shifts towards the left and it becomes higher. This could be particularly useful for certain applications where the load may require much higher initial acceleration torques for a smaller amount of time. Last, let's take a look at the effect of some of the parameters that we have not discussed throughout this presentation so far. Let's look at the effect of the core resistance and magnetizing reactance. If we vary the most of the time negligible core resistance to a much higher value, in this case 20 per unit, we can observe that there is almost a negligible change in the current and motor torque. We will literally have to lower the core resistance to approximately 5 per unit to start to observe an effect on the motor characteristics. In this case, the main effect is a higher current consumption. What this effectively says is that the starting characteristics of this motor will be almost unaffected. However, its long time performance running under full load conditions will probably cause a much lower efficiency and much higher losses. This will result in a very inefficient machine. In the same fashion, we could return to the previous motor before we change the parameters and now proceed to change the magnetizing reactance. If we applied a 50%, we should be able to observe again that now the current also increases. However, this time the increase in current is not that of an increase in active power, it will be an increase in reactive power. That means this motor will operate under a much lower power factor. If we continue this down to a very small magnetizing reactance value, which would be very uncommon, we could observe the continuous trend in the increment in current. This means that for the most part, the effect of the core resistance and magnetizing reactance is negligible for squirrel cage induction motors. Now we can proceed to look at some of the characteristic curves and the key points that are used by the industry to design or to represent these particular curves. As we saw in the previous discussion of the effect of each parameter on the individual characteristic curves, the effect of each parameter can be significant. This slide provides a very basic list of the key points in these characteristic curves, which are used by the industry to describe induction motor characteristic curve behavior. Here we can see that we have what the industry calls as the lock rotor torque, which is the point at which we call a lock rotor condition and in which we deliver the starting torque characteristic of the motor. We also see the breakdown torque, or otherwise known as the maximum motor torque. Next, we see the load torque and its different characteristics. The load torque represents the mechanical torque drawn by the load, and it can take on different shapes and different characteristic demands. It can be a fan, it can be a pump, it can be a crane, and so on and so forth. The shape of this load torque curve is defined by the type of an application that is required for this motor to drive. Next, we see the current characteristic, and as we saw in the previous editor, we have the lock rotor current and how it changes from the lock rotor current conditions towards normal full load operating conditions. And we also see that we have a base, which is usually represented as the full load amps of the machine, and the base for the torque is usually the motor rated torque. Last, we will see common terms in the industry as the lock rotor power factor, and the lock rotor power factor pretty much just tells us what is the power factor of the motor throughout the acceleration behavior of the machine. As we can see, during the starting conditions, we have the lowest lock rotor power factor. Therefore, we expect a very high reactive power demand from the motor. This slide is similar to the previous one, but introduces a couple of different concepts. The concept that is introduced in this slide is that of the acceleration torque or the acceleration power. The acceleration torque is defined as the difference between the motor torque and the load torque, and it provides the energy required for this machine to change speed over time. The higher this acceleration torque is, the faster the motor will reach its rated full load speed. We also observe in this slide that we have a point common for the load torque and the motor torque. This is what we call the rated full load torque of the machine, and we also observe that at the rated full load torque operational value of the machine, we determine what is the equivalent rated full load amps of the motor. This common point, where we get the rated full load torque and full load amps, is what we call as the rated full load slip of the motor. In this case, we're representing the motor starting characteristics as a function of time. But if we were to represent them as a function of slip, this point in particular will be designated as the rated motor slip. Now we can discuss the basic models which are available to simulate the dynamic behavior of induction motors and their particular purpose. The most basic and yet the most important type in most applications is to determine the voltage drop, which occurs when we accelerate the motor. As we discussed in the previous slide, we expect a very high lock rotor current, which will proportionally cause a very large voltage drop in our system. When we connect the motor to the electrical network, we'll draw a lock rotor current, which is composed of the active and reactive components, and therefore we'll have a large voltage drop across our system. This voltage drop will be proportional to the lock rotor current that is drawn. This lock rotor current changes depending on the design of the rotor and the changes in resistance and reactance of the bars. NEC assigns different code letters to different types of motors and different types of horsepower sizes to represent the relationship between the lock rotor current and the full load current. In this case, we have an example for NEC code letter where we see that it's a 6.5 value, which represents a ratio of 6.5 times current at lock rotor current conditions with respect to the rated full load amps. Using the knowledge, we can do a quick example where if we have a 100 horsepower motor with rated 460 volt line-to-line voltage and a rated 80% power factor, 90% efficiency, and a 650% lock rotor current, and a 20% lock rotor power factor, we could use this information to determine what will be the power consumption at that rated motor voltage during starting conditions. We can observe that following the basic calculations that the reactive power would be about 11 times higher during lock rotor current conditions. This particular calculation is what we call static motor starting in ETAP. And in essence, it is the very first and most basic motor starting analysis that is done in the industry, but yet, as I mentioned before, the most common. It allows us to know what is the voltage drop in the system and therefore what is the voltage at the motor terminals. The information on this voltage drop will allow us to, for the most part, determine whether this motor can start based on the information that we have available from the manufacturer. This particular graph shows an overlay of the motor current drawn during a static motor acceleration simulation and a dynamic motor acceleration condition. This slide comes from the ETAP help file, and it also helps us to visualize the difference between dynamic and static motor starting. Of course, the most obvious difference is that the actual acceleration time is not determined by the static method, and it must be provided as an input to its simulation. The static motor starting method cannot determine the acceleration of the motor, only the voltage drop in the system. Next, we will proceed to discuss another method that is available in ETAP and which is the most comprehensive, and it will be used not only for motor acceleration, but it's also used for deceleration under both closed and open circuit conditions. To introduce the third method available in ETAP to model induction motor acceleration, we must remember a few things. First, in reality, there are three phases with a rotational oscillatory frequency determined by the system. These phases, for the most part, are assumed to be balanced. However, this is not a requirement of this method. But for the most part, in the transit stability and motor acceleration simulations, we assume that the input stator voltages are balanced. Furthermore, each phase is generating individual magnetic fields. Each magnetic field from the stator induces a current and voltage in the rotor and a field that wants to align itself with that of the stator. If we analyze all three phases, we would need 6 different flux linkage equations to represent each stator-phase interaction. This would make the analysis very cumbersome. However, thanks to many researchers including Parks, Kovacs, and Drax, the analysis can be simplified into 2 flux linkage equations, one for the rotor and one for the stator. Using the assumptions of symmetry of the windings, and this is very important, this means that each phase has to be equally distributed along the stator. We can also make assumptions to neglect saliency, saturation, and magnetic saturation, as well as representing both the stator and rotor circuits using a common frame. In this case, the most common frame to be used is that of the stator. We can convert the three-phase model to a direct and quadrature axis model, which simplifies our simulations tremendously. Now we only have to deal with 2 equivalent magnetic fields, and we can use the stator magnetic field as the reference for the simulation. The main benefit of the DQ model is that it allows us to determine the effect on the motor, torque, and current when 2 independent circuits' magnetic fields interact with each other at different frequencies. In this animation, we will observe that what happens as 2 magnetic fields interact with each other at different speeds. During high frequency difference, which is the point at which we start a motor, the leakage reactance is high and the torque direction can be even negative, as the 2 fields are trying to align to match the stator frequency, minus a small speed difference, which is represented here as the slip angle. Of course, the slip angle will be high because the stator frequency will be much higher than that of the rotor during initial conditions, and this slip angle will reduce to a small angle once the motor reaches operational speed. The interaction of these 2 magnetic fields is especially important for open circuit bus transfer analysis, and this is one of the main benefits of the DQ model, is that it allows us to observe the interaction of the motor torques that can be generated in the rotor and the stator, because we want to make sure that when we reclose the motor to its alternate source, that we do not close the motor at a point where both magnetic fields will be opposite in both magnitude and angular position. The main concept is that the stator magnetic field will be oscillating at the system frequency during initial conditions. Once that stator magnetic field interacts with the rotor bars, it will generate a counter magnetic field which will produce the mechanical motion of the rotor. As this rotor continues the acceleration, the leakage flux, which is the difference between the rotor and stator magnetic fields angle, will become smaller, and therefore the current will reduce over time. Last, as they both reach very close speeds, there will almost be no leakage flux and the current will reduce to normal full load operating conditions. The DQ model for induction motors gives similar results as the previous 2 dynamic acceleration methods. Of course, in the case of comparison to the static motor starting, we would only be referring to the voltage drop at the time at which we start the motor. The DQ model is typically used for stability studies, and as I mentioned before, this would include fast bus transfer conditions. The DQ model is a good model for reacceleration and deceleration, not necessarily only during fast bus transfer, but also during cases where the system frequency dips down or increases, we would like to also observe what happens to the motor during these conditions. The DQ model can be used to predict motor current contribution to a fault on the system side as well. And the DQ model can be used to predict motor behavior with unbalanced voltages. However, in transient stability, we still assume that the input stator voltages are balanced. This slide shows the equivalent transfer function diagram of the induction machine in DQ model representation, with the stator being used as the reference frame. As we can see, we are integrating both the stator and rotor flux currents to determine their respective magnetic fluxes. The flux linkage relationships allow us to relate the different inductances of the motor to the flux and current. In the next simulation, we will observe the dynamic behavior or characteristic starting curves when the DQ model is utilized for starting an induction motor. As we will observe, it is slightly different from what we have seen in the previous parts of this webinar. This particular system is a UDM created induction motor in DQ reference frame using the stator as the reference. It also includes a mathematical model, which is a single mass model formulation to determine the motor mechanical speed and the mechanical load, as we can see in this region. In this portion of the model, we can observe the electrical circuit diagram and the portion of the model that calculates the flux and current relations between the rotor and stator. The model also includes a couple of items that we will discuss in a few minutes related to the starting devices and adjustable or variable frequency drives, which can be used to control and start induction machines. However, first, let's start with a bypass of the drive and controls to simulate a direct across the line start using the DQ model. As we will see, when we start a motor using the DQ model across the line, we will get an initial high difference between the rotor and stator frequencies. This will generate a lot of torque interaction and a high current in the rotor circuit. Here we can see the motor torque, and we can also see the stator current. I would also like to highlight the motor speed and the motor slip, plus also the acceleration torque. We will look at some of these individual plots in more detail, starting with the motor torque. As I mentioned before, the DQ model allows us to observe the motor torque and current interactions as the machine accelerates. In this case, we can see that during the initial stages, right after the motor accelerates, that we have a high motor transient behavior, which represents the conditions that we described. And as the rotor builds speed to approximately 30 or 40% of its rated speed, the rotor and stator fields aligned and the torque interactions are more controlled. At this point, the motor proceeds and receives a similar operating characteristic as to what we saw in the previous parts of this webinar, where we can identify the maximum torque and the full load torque of the machine. In the same fashion, we understand that to generate this motor torque, we need to have current flowing through the rotor bars. In this case, the current also experiences high fluctuations during the initial stages of the acceleration. As we can see in the DQ model current plot, we can observe high initial current fluctuations during the initial stages of the acceleration. And we observe that these current fluctuations start to reduce at a similar point once the machine has reached a certain speed. After that point, the current at the full load conditions is very similar to that of the regular dynamic acceleration model. The last point or graph that I would like to highlight from this simulation is that of the acceleration torque. And as I mentioned before, the acceleration torque is the difference between the motor torque and the load torque. And in this case, the interaction of the rotor and stator produce a high changing motor torque condition, which for the most part is positive. Therefore, it does accomplish the mechanical acceleration of the rotor mass. However, during initial conditions, we do see high transient conditions, even some points during which there are slight deceleration periods where the acceleration torque becomes negative. However, the motor does successfully reach its operating conditions and the acceleration torque goes to zero as the machine is running at steady state conditions. So as we have observed, the DQ model allows us to observe the transient interactions in the current and torque in the motor, in particular at situations where the frequency difference between the rotor and stator is high. Next, we will look at starting devices, and we'll come back to the simulation to observe how starting devices, including reduced voltage starters and variable frequency drives, will affect the behavior of the motor modeled using the DQ model. The starting devices in ETAP, which can be applied to induction motors, are shown in this particular slide. The starting devices can help to start the motor with reduced voltage conditions, and they can also reduce the current. The large majority of starting devices are applied to minimize the effect of the large voltage drop which occurs when we start a motor, and as we discussed in the previous parts of this webinar. Here we can see that we have reduced voltage, megavar support, rotor impedance, different types of winding arrangements, soft starters, and last, the variable frequency drive or adjustable speed drives, which are the most complex. The starting devices for induction motors can be accessed through the starting device page of the induction motor editor in ETAP. We do not have time to discuss in detail each of the starting devices and which is most appropriate for each particular application. That would take an entire webinar session just to discuss in detail. However, we will be able to see the effect of a few of the starting devices and most importantly the effect of variable frequency drives as we apply them to our induction motor examples. Next, we will take a look at some adjustable speed drive and soft starter simulations. As we saw in the previous example where we started an induction motor across the line, we can also apply different types of soft starters as starting devices to reduce the voltage drop in the starting process of the motor, or we could also use adjustable speed drives to help us control the motor speed during normal operating conditions and also to reduce the voltage drop during starting conditions. In this example, we can take a look at how an adjustable speed drive can accomplish both conditions. First, let's start by simulating a simple soft starter where we will apply a reduced voltage ramp condition for approximately 4 seconds and we will start from approximately 0 voltage and we will end up at rated motor terminal voltage. In this simulation, we will be able to see how the DQ model induction machine reacts to a ramp change in the input voltage. Here we can observe the plots, which are quite different from the plots that we observed in the previous simulation. Here we have the stator current, and we also need the acceleration torque, and we need the motor torque. I'll also like to highlight the slip and the speed of the motor. Before I look at those individual plots, I'd like to explain that we're applying a reduced voltage starter that goes from 0 voltage at 1 second and applies full voltage 4 seconds later to the motor stator. First, let's look at the reduction in the stator current. There are two things that can be observed from this stator current plot. First, unlike the previous simulation, we do not notice any high current changes in the current drawn by the motor. This is caused by the reduced voltage applied to the stator. This accomplishes a reduced voltage drop in the system as we accelerate the motor. We can also observe that the motor torque increases proportional to the increase in the applied motor voltage. In this case, we can see that we start from almost no torque, and as the voltage increases, the torque increases proportional to the change in voltage square until it reaches the full load torque. Since we do not have any high change in initial current during the periods of time in which this motor is building speed, we do not expect any high current flux fluctuations between the rotor and the stator. Therefore, we do not observe any high transients in the motor torque. Here, the speed plot and the slip plot both confirm that the machine accelerates in approximately 4 seconds. Next, we would like to take a look at how a variable frequency drive would be performing for starting the same motor. In this case, we can change our mode of operation of our drive from a reduced voltage starter to a variable frequency drive, in which we will start from 0 voltage and frequency, and using a constant volts per hertz relationship, we will ramp up both frequency and voltage to rated 1 per unit voltage and frequency. We will be able to observe the behavior in the reduction of the motor current and the controlled acceleration torque because of the reduced frequency applied by the frequency controller of the drive. First, let's pull up the stator current, as we can see right here. We'll also use the motor torque, and we'll bring as well the acceleration torque and other related plots. We'll also utilize the slip and the speed of the motor. Before I get to the characteristic curves of the motor, we'll look at the applied frequency and voltage. As we can see, at t equals 1 second, we start the application of both the voltage and the frequency, and we observe that we keep a close constant volts per hertz ratio from equals 1 per unit, and we ramp from 0 to 100%. The important control item that we want to highlight in this simulation is the fact that the stator current has been significantly reduced. We observed in the previous across the line simulation that our current was approximately 4.5 to 5 times the full load amps. In this case, the motor current has been reduced and changes by no more than 150 to 175% of the full load amps throughout the entire acceleration period. We can also highlight the reduced transients in the motor torque, as we can see from the motor torque plot. As previously discussed, when we reduce the frequency between the rotor and stator magnetic fluxes, we reduce the high torque transient conditions in the motor. Therefore, in the variable frequency drive operation, when we have a closer or a smaller angular difference between these two magnetic fields, we reduce the transients significantly and therefore provide a more smooth and controlled motor torque application to the load. Last, I would like to highlight the acceleration torque of the machine, and we can see that it's pretty much an average value of approximately 0.25 to 0.3 per unit of the motor rated torque. This is accomplished by using a variable frequency drive with volts per hertz constant application. There are other types of controllers which can be created using UDM. We could create torque control, vector torque control combined with frequency control and speed control, and we can also create types of drives which are combinations of both. However, for the most part, a basic variable frequency drive model is available in the built-in ETAP model. This model, created in UDM, was created for the purpose of visually illustrating the components that are included inside the built-in model of the ETAP dynamic machine model. Next, we'll like to talk a little bit about the final dynamic transient behavior, which is the fast bus transfer condition and the requirements for the DQ model in that simulation. The dynamic behavior of the motor during deceleration conditions is of particular interest in this presentation. As we discussed previously, the rotor currents produce an internal magnetic field which is still present when we disconnect the power supply to the motor. As mentioned before, the DQ model allows us to see the interaction between the core magnetizing reactance and the rotor bar resistance and reactance. The interaction of the remaining magnetic energy in the core with the rotor circuit creates a decaying voltage in the rotor. The friction and load also decelerate the rotor and therefore start to increase the angular difference between the internal rotor voltage phasor and the alternate source voltage. This slide shows what happens to the rotor current, voltage, slip, and acceleration power when the machine decelerates during disconnection of the original source, and what happens to the motor as it is reconnected to the alternate source. In this particular case, we can observe that the internal voltage of the motor goes from approximately rated voltage down to approximately 35%. When this occurs, and as the internal rotor voltage goes down to approximately 30 to 20%, we can consider this to be a residual bus load transfer. Under such conditions, the starting current will almost be the same as that of a motor starting from standstill conditions. However, the concern in the majority of the simulations involving bus transfer with induction motors is the fast bus transfer. This slide shows an spiral decaying internal motor voltage. This spiral decaying motor voltage represents the internal voltage of the motor as a function of time. The decaying magnetic field causes a decaying magnitude. The decay in the internal voltage is determined based on the motor open circuit time constant, which is determined mainly from the core magnetizing reactance and rotor bar reactance and resistance. The core resistance losses are typically negligible in this condition. Motor fast bus transfer is defined using the following conditions. First, the transfer time is typically a lot less than 10 cycles. In the majority of cases, 3 cycles is the target time. The angle between the internal voltage and the alternate source voltage should be less than 90 degrees. If we meet both conditions, we should have a resultant voltage difference phasor between the internal motor voltage and that of the alternate source equal to 133% or less of the motor rated voltage. If we allowed this resultant equivalent voltage applied to the motor to be higher than this, we run the risk of damaging the stator windings and the motor shaft because of high transient torque conditions. As we discussed before, the DQ model is required for modeling deceleration since it allows us to keep track of the power supply and the rotor internal flux and current. This slide shows what happens to the torque and current if the motor is never reconnected to a source. The next topic in this webinar deals with the most difficult part of induction machine modeling. This part tends to be the selection of the motor circuit parameters, which sometimes are unknown and sometimes have to be estimated, or sometimes are provided, yet we need to increase their accuracy to match the manufacturer provided curves. The last section of our webinar today will focus on the machine parameter estimation process, which is very important for our system analysis involving dynamic motor behavior. As we have seen in this webinar, several parameters have a profound effect in the motor dynamic behavior, with the stator and rotor resistance and reactance being the most notable. With induction machine parameters, there are two main issues. The first one is that the circuit parameters are not readily available, but only a few of the key parameter values are available in the motor documentation. The second issue comes when the manufacturer actually provides both the circuit parameters and the characteristic curves, which is typically a good thing. However, the simulated results do not match those provided by the manufacturer. There are two solutions in ETAP to deal with both problems. They are two modules called PE, which stands for Parameter Estimation, and MPET, which stands for Motor Parameter Estimation and Tuning. The first module, called PE, can be used to estimate the equivalent circuit parameters by using a few of the key characteristic curve points which are readily available. These parameters are taken from the nameplate and impedance models of the induction motor editor and ETAP. As we can see in this slide, some of the key characteristic parameters taken from manufacturer datasheets are shown in the respective ETAP editors. The key commonly available required parameters for the parameter estimation simulation are the lock rotor current, lock rotor torque, lock rotor power factor, maximum torque, rated full load current, rated power factor, and rated slip. These parameters are currently highlighted with red dots in this characteristic curve set of plots. Once these parameters are entered into the induction motor editor in the respective nameplate and impedance model pages, ETAP parameter estimation can use them to estimate the equivalent circuit parameters by means of the parameter estimation and tuning editor, which is accessible by clicking on the parameter estimation and tuning button that we see in this particular image. Once clicking on that parameter estimation button, we get the parameter estimation editor. This PE editor shows the nameplate, input parameters, and uses a proprietary partial derivative and parameter sensitivity analysis to determine the equivalent motor circuit parameters, or circuit parameters that are required for dynamic simulations. At the same time, the parameter estimation tool provides the deviation between the given input and estimated values. This deviation can be used to visually check the accuracy of the estimated solution. The equivalent circuit model can then be used for motor acceleration in both motor acceleration and transient stability modules. Here we can see the estimated results, which can then be automatically loaded back into the induction motor editor to replace the current initial input parameters and also to provide the much needed circuit model parameters required for dynamic simulations. Before we show that process, I would like to highlight the calculated parameters which were derived based on the estimated circuit parameters in this region, and I would also like to highlight the deviation which was obtained. As we can see, this deviation is relatively small, not higher than 0.09% or approximately 0.1% in the case of the efficiency at full load operation of the motor. Once we have evaluated these parameters, we can proceed to determine whether we can update some of our existing parameters within the induction motor editor. In most cases, the majority of our users choose to only update the circuit parameters and retain the original manufacturer provided nameplate values. This is good practice to preserve the integrity of the basic low flow and short circuit results which are used for ANSI standards, but at the same time take advantage of the model data for the squirrel cage induction motor, which can then be used for our transient and dynamic motor behavior simulations. Here is how the editor will look in the final circuit model parameters being selected. Once we have selected those parameters, whether we update and replace the short circuit or nameplate data, or we choose to only update the equivalent circuit model parameters, we can observe that this editor shows the estimated parameters in this window on the upper left hand corner with a corresponding set of characteristic curve data which was generated based on the estimated circuit parameters. On the right hand side, we have a set of 3 plots which represent the motor torque, motor current, and motor power factor as a function of the slip. This will conclude the parameter estimation process based on the key characteristic curve data points. However, as we discussed before, there may also be other types of motor parameter data collection problems. The second type of these characteristic issues that we may encounter when we are simulating the acceleration of motors can be when the manufacturer actually provides the characteristic curves and also the circuit parameters that can be used to simulate the motor. At the same time, when evaluating the differences between the estimated and calculated simulation results, we can observe that at some regions in the characteristic curves, there may not be an exact match as accurate as we would desire. Here's another example of manufacturer provided characteristic curves In this case, we have both the motor torque and the motor current in percent of their respective bases. We see the motor and current torque provided at 100% of the motor rated voltage and at 80% of the motor rated voltage. However, the most important example in this group of manufacturer datasheets that we have selected for these slides is the one that we show in this particular case, where we can observe certain behavior around the pinch point of the motor torque curve. This pinch point, or what otherwise is known as, in common terms, the belly of the curve, sometimes can have different inflection values. It could be a little bit lower than what's shown right here, or it could be what we have in this particular curve. At the same time, once we get past the inflection point of the motor torque characteristic, we get up to important data points before the maximum torque and right after the maximum torque. This region of points is also important to determine the acceleration torque for certain types of motor loads which require high load in some applications. It is because of this particular problem that we have a new estimation engine which enhances the process, and it is called the motor parameter estimation and tuning. Here's how the motor parameter estimation and tuning process works. First, we take the manufacturer characteristic curves and all the data points that were shown on the previous slide. All that information is entered into the motor library, into the characteristic curve library of ETAP, and then it can be selected through the library's options inside the editor and loaded into the model page of the induction motor. After we have selected that from the library, the characteristic curves from the library, we can proceed to select the particular manufacturer and model that we are going to use for the estimation. As soon as we select it, we can observe the characteristic curves for the torque, for the current, and the power factor. From there, the MPIT estimation engine can take many more data points at different predetermined intervals as additional data to be considered in the estimation of the rotor and stator resistance and reactance. The highlighted points indicate all the available data points that can be entered into the motor characteristic circuit library, which can be taken from the manufacturer provided characteristic curves. The highlighted flashing points here show some of the areas of special interest in the estimation, which cannot be considered using the regular parameter estimation approach. As we can see, the flashing highlighted points are near the belly of the curve, or the pinch point. The next set of flashing points represents areas where we may also need higher accuracy in the motor torque representation for dynamic studies. Once the curves are loaded, the MPIT editor does still show only some of the key parameters, similar to how the parameter estimation module was presenting the input data. However, it still considers all the other additional data points which were highlighted in the previous slide. Using a combination of these key parameters and all the additional data points taken from the manufacturer data curves, the MPIT editor proceeds to perform an estimation to determine the equivalent circuit parameters for this machine that will match all the data points that were provided from the library and from the nameplate and impedance model pages of the induction motor editor. The estimation results are obtained within a few seconds. However, in the background, the MPIT proprietary particle swarm optimization engine performed thousands of estimations to find a nonlinear set of approximately 21 parameters which represent the rotor resistance and reactance change as a function of the motor slip. As we learned during this webinar, the construction of the rotor bars or the single or dual cage designs can have a profound influence in the effective resistance and reactance of the rotor as a function of the slip. The magic of the particle swarm optimization method cannot be observed by the elegant simplicity of this editor, as it estimates this additional set of data points which represent the nonlinear characteristics of the rotor. The following slide will show us a video where we can visually appreciate some of these internal calculations performed by this optimization engine. The particle swarm optimization method is an stochastic estimation engine which can iteratively eliminate solution parameter combinations until it arrives at the combination of parameters which produces the closest match to the provided manufactured curve data points. This video shows how the particle swarm optimization method eliminates random particle combinations until each of the data points along the motor torque and current are close to those provided by the manufacturer. Note that the particle swarm optimization process simulation shown here can be applied to many other applications, including other machine and controller parameter estimation and tuning. To reiterate, in this particular video we can observe the load reactive power component, which can be equated to the motor current, and the load real power demand, which can be equated to the motor torque. Under these conditions, until the simulation finds all the equivalent parameters matching, the simulation will stop within its desired error deviation and it will give us a final solution. Finally, after the MPET or motor parameter estimation and tuning estimation is done, the estimated characteristic curve and the manufacturer provided curves are displayed on top of each other to aid in the visual evaluation of the estimation engine performance for the whole acceleration period. Similar to the parameter estimation module that we described earlier, there are a few steps that we skipped where we actually select the parameters and we choose to update them into the editor. The same process would apply. Here we show the updated parameters back into the Induction machine editor, and we show an overlay of both the calculated and the given manufacturer parameters. As we can see in this case, and in most cases, there is negligible deviation between the estimated calculated curves and the original input data. The given and the calculated curves almost overlaid each other perfectly, which represents very low deviation in the estimation process. The same thing can be observed in the motor current estimation, where only a slight deviation can be found near the maximum torque point at the point where the current starts to go towards the full load amps of the machine after the machine has accelerated. Wow, I know that I have provided a lot of information in this webinar. However, its main intent was not to cover in detail all the fundamental concepts related to induction machines, but only to provide a high-level overview of the many fundamental principles applied by ETAP to model induction motors. Based on the contents of my presentation today, we can arrive at the following conclusions. Induction motor type and the rotor bar construction and the number of cages determine heavily its dynamic behavior. ETAP models vary in complexity according to the simulation needs. Examples are the static motor starting, the dynamic motor starting, and the direct quadrature axis models, which are used for advanced transient stability studies. For system transients involving fast bus transfer, the DQ model is needed to model internal torque, voltage, and current interactions. This is very important to be able to determine at what point we can reclose the breaker without causing extremely high internal torques on the motor components. Starting devices can be modeled through built-in library models, which can be selected through the induction motor editor, very simply through the starting device page in the motor. Or we can use our creativity and create any kind of complex starting device element with the help of the user-defined dynamic model or UDM module. We can also conclude that manufacturer-published characteristic curves can be more accurately matched with the use of nonlinear rotor resistance and reactance models. This is very important when we require high accuracy in the matching of motor characteristic torque curves and load curves to determine if we can actually accelerate the motor. I would like to thank you today for taking your valuable time and listening to this webinar. I'll stay here for the next few minutes to answer any questions that you may have. Thank you very much.